grab your calculator. You're going to need it as we work through these complex numbers. We're going to be doing the trig or the polar form of complex numbers in section 8.2. Now, if you have looked ahead a little bit, you'll have noticed that we're going to do the next few sections out of order. We're doing 8.2, and then we're going to move to 8.5 before we can pick up 8.3 and 8.4. So 8.5 is stuck out of order for chapter 8 because I just really feel like it fits better there. Okay, this is typically a new topic, polar form of complex numbers and polar graphing, as well as just graphing imaginary numbers. So, the complex plane and vector representation. To graph a complex number, such as that standard form 2 minus 3i, where we have a real part and an imaginary part, we're going to modify our coordinate system by calling the horizontal axis, instead of just the x-axis, that's going to be my real axis, where I graph the real part of my number, and the vertical axis is going to be my imaginary axis, where we graph that imaginary part of our number. Then our complex numbers can be graphed in this complex plane, as shown in the figure. So we've got our horizontal axis as the real axis, our vertical axis as the imaginary axis, and when we are graphing this number 2 minus 3i, we go to positive 2 for the real part and negative 3 for the imaginary part. That is where my vector will terminate. Now, a vector is just a directed line segment. So I start at the origin and I draw an arrow out to that point, to negative 3. Each complex number determines a unique position vector with the initial point at the origin and the terminal point at whatever those values are for the real part and the imaginary part. Remember, this is a plus or minus bi, that standard form for my complex number. This geometric representation is why a plus bi is called the rectangular form of a complex number. The rectangular form is also called the standard form. So rectangular form and standard form are used interchangeably. So rectangular is also the standard form, and that's my a plus or minus bi form. Just kind of keep that in your mind. Okay, so we're going to practice graphing. We are going to find the sum of two complex numbers, graph them, and their resultant. Now, their resultant is just the sum. So I'm going to graph 2 plus 3i. I'm going to graph negative 4 plus 2i. And then I'm going to graph the sum of those two numbers. So let's find the sum first. The resultant, or the sum, is going to be 2 plus 3i plus negative 4 plus 2i. Remember, we combine our like terms, so our real part is a negative 2, and our imaginary part is a positive 5i. That's going to be my resultant. Okay, so first, let's graph our numbers. We're going to graph 2 plus 3i, so 2 is the real part, 3 is the imaginary part, and right there, that is my vector form of 2 plus 3i. Remember, this is my real axis, and this is my imaginary axis. Then I'm going to graph negative 4 plus 2i. So a negative 4 for my real part, positive 2 for my imaginary part. That's where my vector will end here. I did not grab a straight edge. I may need to do that here in a minute. So that is my second complex imaginary number. And now I'm going to graph the resultant, negative 2 plus 5i. That's where that vector will end. And you can see that I get this kind of polygon in here, which reminds us that this is my rectangular or standard form. Now that resultant should always fall in between those two initial complex numbers. Okay, so practice on this next one. Pause the video. You're going to do the same things. You're going to graph each of the original complex numbers, and then you're going to find and graph the resultant. Pause the video, see how you can do it on your own, and then come back to see if it matches mine. If I can find the straight edge, there we go. And we've got -4 minus 3i. There's that vector. And our resultant, 2 and a -5i. There, and you can see again we've got that polygon formed between, reminds us that this is the rectangular form of my complex numbers. Alright, so I always enjoy doing the polar form, moving from complex graphing to the polar form of the graphing. So that's what we're going to do next. We're going to start out by defining some relationships. Now these relationships are important. You're going to need to tie them in together in your mind. You'll use them for this last unit, for this last chapter. You will see them again in Trig and Pre-Cal. So when I am switching from my rectangular or standard form to my trig or polar form of my complex imaginary numbers, I need to remember relationships between these values, x, y, r, and theta. Now, we know this is my Pythagorean theorem, right? R squared equals x squared plus y squared, so r would be the square root of that sum. And I know that x is cosine theta. Now, if I'm on the unit circle, it's just x, but if I'm not on the unit circle, we've got cosine theta is x over r. Now, on the unit circle, my radius is 1, so that's just equal to x. But if I'm not on the unit circle, if I'm anywhere else, that value r, to solve for x, I would multiply that over here. Even if r is 1, that's what I do. I multiply it over. Okay. Sine theta is y over r. So when I solve for y, I multiply that r over. So y is equal to r sine theta. These two relationships come directly from our right angle trig, or our standard position trig definitions. This one is based on our Pythagorean identity, Pythagorean theorem, and then tangent theta is y over x. We know that as well from our definitions for our trig functions. So one thing that we're going to do new is that r, instead of our radius, is going to be called our modulus. We think of it as the absolute value of x plus yi as our complex number. And we're going to remember that this relationship here for tangent is what is going to allow us to find theta. This relationship y over x being tangent allows us to find theta. So remember, keep in mind that our sketch of our angle in standard form, we've got x, we've got y, we've got r, and this is our angle theta. So when we know x and y, that's what we're starting with, we use it to find r, and we use it also to find our value for theta. Okay, so our standard rectangular form for our complex imaginary number is a plus bi, or we can think of it as x plus yi. Our trig or polar form of our complex number is this expression, r times the sum cosine theta plus I sine theta. So this is my trig form, or I can call it my polar form of my complex number, x plus yi. Now notice I've just replaced a and b with x and y. This expression, cosine theta plus I sine theta, that gets kind of lengthy to say. So I will abbreviate that as CIS theta. CIS theta. That's my abbreviation. Using this notation, I would write it as R CIS theta, because we have R times that sum cosine theta plus I sine theta. So this is my shorthand. This is my abbreviation for my trig or polar form. Just one more time to get it in one place for you. You have a rectangular or standard form of your complex imaginary number. That's my a plus bi or x plus yi. And you have a trig or polar form of your complex imaginary number, and that is your r CIS theta, or r times cosine theta plus I sine theta. So those are our two forms for our complex numbers. Now we're going to go back and forth. We're going to practice using these going back and forth. We're going to go back and forth using these relationships that we have defined and discussed. All right, so what form am I in? Well, I'm obviously in my polar form because I've got a value r, and inside parentheses I've got that sum cosine theta plus I sine theta. It's evident that theta is 135 degrees. And because of the definition of this polar form, I know that r is 10. So let's plug in what else we know. Well, I know that 135 is an angle on my one of my special angles on my unit circle. One of my special angles on my unit circle. It's a 45 reference angle. So my sine and cosine values are both square root 2 over 2. Because it's in quadrant 2, that cosine function value is negative. So I'm going to plug in what I know. I've got 10 times a negative square root 2 over 2 plus I times that positive square root 2 over 2. And then algebraically, I distribute. So when I distribute the 10 here, it's going to reduce, and I have a negative 5 square roots of 2 plus a positive 5 I square root 2. And now I'm in my rectangular form. X plus yi, or a plus bi. Now keep note, again, when we write our standard form, that I is at the end, but we don't put that I behind a radical because it just gets messy. It's difficult to make sure we have it spaced correctly, so we usually put it out front with a coefficient. Alright, one more to practice on here. We see that we're in trig form because we are given CIS theta in parentheses. That means that r is 2 and theta is 300 degrees. Again, a special angle on my unit circle. This one has a reference angle of 60 degrees. So what's my 60 degree reference angle? Well, it's the value's 1/2 square root 3 over 2, except I'm down here in quadrant 4, which means that sine function value is negative. Substitute what I know. Cosine at 300 is a positive 1/2. Sine at 300 is a negative square root 3 over 2. So I'm going to say negative square root 3 over 2i. I sine theta. There's my negative square root 3 over 2. And then I distribute because algebraically that's the next step. Half of 2 is 1 minus, and those 2's are going to cancel, so I just have I square root 3, and that is my rectangular form of the trig form that I was given. So I'm just switching back and forth. You remember in college algebra we would talk about inverse operations, and that exponential functions and log functions are inverses of each other, and you just have 3 pieces of information, you switch them back and forth. We're just switching back and forth from one form to another. This form and this form represent the same value, the same location. It's just a different way to write it. Okay, so when I am converting back and forth, if those of you who like that step-by-step table, here you go. Converting from rectangular to trig form. Sketch your graph of x plus yi in the complex plane. Find r by using the equation r equals square root of x squared plus y squared. Now, we were going from trig form to rectangular form. That's super easy. If I'm going from rectangular form into trig form, it takes a little bit more work. I start with a sketch. Always start with that sketch so you know what quadrant you're in. Then you find that value of r using Pythagorean theorem. And then you find theta using that value for tangent theta as y over x. Because you know y and x, you can figure out which angle theta would be. Again, you got to make sure you're in the right quadrant, so you have to have created your sketch. So sketch, find r, find theta. Alright, let's do some examples converting going that direction. We're going to write each complex number in trig form. So we're starting in rectangular form, we're moving to trig form. That means that my first step is going to be a sketch for each of these. So I'm going to set that up so that my first step can be a sketch for each of these 4 examples. On this first one, I've got 8 minus 8i. My real part is a positive 8. My imaginary part is a negative 8, so that's going to be that point right here, and there's my vector, my directed line segment. This is my angle theta that I'm interested in. I've got my sketch. My next step is to find r, square root of x squared plus y squared, so 8 squared plus a negative 8 squared. 8 squared is going to be 64. 64 and 64 is the same thing as 2 times 64, and that 64 square root is 8. So I've got 8 square roots of 2 for my value for r. My third step is to find theta. So I'm going to use tangent theta, y over x, negative 8 over 8. So my tangent function value is a negative 1. Well, what angle in quadrant 4 has a tangent function value that is negative 1? Well, that's anytime the x and the y are the same and I'm in quadrant 4, you're looking at that 45-degree reference angle. So I've got 315 degrees or 7 pi fourths. I did not give you instruction over whether to use radians or degrees. You know what? Let's do radians on this column and degrees on this column. So we'll do A and C in radians, we're going to do B and D in degrees. Just to emphasize that it doesn't matter, we can do either. Well, we said, okay, that means that's that quarter angle in quadrant 4, that's going to be 7 pi fourths. So now that we know r and theta, we can plug into our trig or polar form r cis theta. R is 8 square root 2. CIS, theta is 7 pi fourths. That's the shorthand version, and that's great. That's fine. If you like to write it out the long way, you're going to have cosine 7 pi fourths plus I sine 7 pi fourths. So we got the shorthand version and the longhand version for our polar form. Okay, let's do one in degrees. Now, I only have negative 15 here. What do I do with that? Well, I need to decide, is that my real part or my imaginary part? And because it does not have an I with it, it's my real part. So that means my real axis, I'm going to move out to negative 15. Negative 15 is right there on my real axis. So there's my vector representing this angle theta. And life just got a lot easier because I know exactly what angle theta that is. If I'm over here on the negative horizontal axis, I'm at 180 degrees. So I've done my sketch. I need to find r, but I just figured out that theta is 180 degrees. I could do tangent theta is 0 over negative 15, so that's going to be 0. But I don't have to because I know that theta is 180 degrees based on the location. Okay, so r is square root of the sum of the squares. Well, I've got negative 15 squared. My imaginary part would be 0i, so 0 squared is just 0. Negative 15 squared becomes a positive, and the square root of that is going to be 15. So my value for r is 15. And then I put it back in my r cis theta form for polar form. So I have 15 CIS 180 for my polar form, shorthand. Long version, cosine 180 plus I sine of 180. And you don't have to do both. You do whichever one you prefer. I'm happy with either one. My math lab will, I think, set it up for you, and so they'll guide you to which form they're looking for. Alright, as always, I encourage you to pause the video. Do these by yourself. Remember, we're doing radians here, and we're going to do degrees over here. Sketch your angle. So I've got negative square root 3, and I, that's going to be just a positive 1. So I'm in quadrant 2. Here's my angle theta. That's my sketch. My value R. Square root 3 squared is 3, plus 1 is 4, and square root of 4 is 2, so my value for R is 2. I need the angle theta in quadrant 2 that has what as my tangent value? Well, tangent is y over x, so 1 over negative square root 3. That negative in quadrant 2, that's great, that's perfect. To put square root 3 in my denominator, that means that it is in the cosine value. So that is going to be right here at 5 pi 6. It's that pi 6 reference angle, 30-degree reference angle, but we're working in radians for this one. So we've got 5 pi 6. You see again why knowing that unit circle is so important. 5 pi 6 is my angle theta. So R CIS theta polar form, or longhand, there we go. Alright, one last one. Let's do negative 3i. We're going to be in degrees over here, just because I said. Up here I had my real part, this time I have my imaginary part, which means my real part is 0. My imaginary part is negative 3, and again, I don't have to do any work to figure out theta because it's one of my quadrantal angles. There's my sketch. I'm going to need to find R, but I know immediately from looking at my sketch that theta is 270 degrees because I'm using degrees over here. Alright, R, square root of, well, my real part is 0, my imaginary part is negative 3, and if I square that I get 9. And the square root of 9 is 3 for my value for R. Now R is the modulus, is always going to come out positive, and it's always going to come out positive because even if x or y is negative, I'm squaring it, I'm finding the positive square root. So R as my modulus is always positive. R CIS theta becomes 3 CIS 270 degrees as shorthand. Longhand form, there we go. Both give me my polar form, my trig form, just emphasizing that you can write it either way. You don't have to do both. Okay, so we converted from rectangular, right here we started from trig form and went to rectangular form. That's easy, we just plug in what we know and simplify. Here we went from rectangular form to trig form. That takes just a little more work because we have to start with our sketch, but we're still using what we know. Now, notice that in this next and last section for this last example, set of examples, we're told that we are going to use calculator approximations. Well, whenever we are told that we're going to use calculator approximations, we make the assumption that we are not dealing with special angles. We're not dealing with our unit circle, so we're going to have to do calculator approximations. We're going to round to 4 decimal places. I forgot to put that in the instructions. We're going to round to 4 decimal places for our calculator approximations. You can see that these two are given to us in trig form or polar form, so we're going to rectangular. These two are given in rectangular form, so we're going to trig form. So let's kind of block off our space here because some boundaries make me happy. Okay, so we're taking from polar form to rectangular form here. And for these two, we're starting in rectangular form, so we need to end up in polar or trig form. Whichever one you want to reference. Okay, so easy way, starting in polar form, we plug in what we know. Well, I don't know the cosine or sine function value of 205 degrees, but what I do know is I have a calculator that can tell me, and I need to distribute the 7 inside. Now, just to stop and think for a second, 205 degrees is in quadrant 3. And in quadrant, in fact, it's going to be right here somewhere. And in quadrant 3, both x and y are negative. So my cosine is going to be negative and my sine function value is going to be negative. I'm going to keep that in mind as I plug this in. So I'm in degrees. I need to make sure I'm in degree mode so that when I use my trig function buttons, I'm in the correct mode. I'm good. I'm going to go ahead and distribute this 7. So I've got 7 times the cosine of 205. Gave me a negative value. That's what I expected. I'm rounding to 4 decimal places. 1, 2, 3, 4. I'm going to need to round up. So that is a negative 6.3442. And then I'm going to distribute that 7 here. So I've got 7 times sine of 205 degrees. And I get a negative 1, 2, 3, 4. I don't round up, so that just is going to end in a 3. So I have a negative 2.9583i. A plus bi, or x plus yi. This is my rectangular or standard form of the polar form that I was starting with. Don't forget your I. Make sure that your algebraic sign plus or minus is correct. Don't forget to distribute your value for the modulus, your R value. Go ahead and do C. Pause, make sure we're still in degrees, so your mode is still correct. Notice that if I change this mode, just to play with it, if I change my mode to radians and I looked at it again, not the same thing. It's still negative, but it's a totally different value. So just make sure you've got it in the right mode. Let me stick it back in degree mode so I don't forget to do that. Okay, find this. 115 degrees is in what quadrant? Well, it's past 90. I'm not to 180, so I'm going to be in quadrant 2. 115 degrees is going to be here in quadrant 2, somewhere right here, which means x is negative, y is positive. So my cosine function value comes out to be negative. My sine function value comes out to be positive. Don't forget to distribute that modulus, and don't forget to include your I at the end. All right. These last two, we're going to keep it in degrees, but we do have to do our steps. I'm going to need to sketch to see where that angle is going to fall. Let's see, so right here, negative 7 plus 2, negative 7, positive 2 puts me right up here, negative 7, positive 2. There's my sketch for theta. I know that theta is in quadrant 2. So again, x is negative, y is positive. My first step is the sketch. My second step is going to be to find r. (49 and 4 is 53. So square root of 53, can't simplify that. And then my next step is going to be to find theta. So I've got tangent theta is y over x, so 2 over negative 7, or a negative 2/7. So I'm going to use, to find theta, I'm going to use my inverse function button, tangent inverse of negative 2/7. Now, tangent is restricted, right? Tangent inverse is restricted. Where is tangent inverse restricted to? Well, tangent inverse is restricted over here to quadrants 4 and 1. So I know when I plug this in, because it's negative, it's going to give me an angle theta down here in quadrant 4. That's not what I need. What am I going to do when I get this angle theta in quadrant 4? Well, I'm going to have to rotate it around. So I'm going to have to move it around to get it in the right quadrant. Alright, let's plug it in and look at that. We're in degree mode. We're going to do tangent inverse. So tangent inverse, we've got a -2/7 is our tangent function value. It's going to give me an angle theta in quadrant 4. So that gets me to -15.9 something degrees, right? To rotate that around, I need to add 180 degrees because my angle that I'm looking for is not in quadrant 4, it's up here in quadrant 2. So I add 180 to move it around to quadrant 2, and this is my angle theta that I actually need. So theta needs to be 164.0546 degrees. Okay, we have everything we need. RCIS theta, where R is square root 53, CIS, and then my angle theta is 164.0546 degrees. There's my polar or trig form for this angle that I started out with in rectangular form. Now notice that if I hadn't sketched my angle, I would not have known that I needed to move this around. Is this an angle that lives in quadrant 2? Absolutely. Quadrant 2 is between 90 and 180. Okay, last one for this section. Sketch your angle. +5, -4 puts us down here in quadrant 4. That's my first step. So this is my angle theta. Second step is to find R. (25 and 16 comes out to be 41. That doesn't simplify. Next step is to find theta. So I know that tangent theta is y over r, -4/5. Now, this theta is in quadrant 4. So when I plug this value into my tangent inverse, it's going to give me an angle in quadrant 4. Let's do that. Tangent inverse of a -4/5. But notice that it gives me a negative angle value, and I have sketched this angle theta as being a positive angle value. So what I get out here is a -38.6598 degrees. That's not what I want to give as my answer though, because I want to give that first positive coterminal angle. How do I get that value? How do I get the positive value for this theta? Well, I need to rotate it a full rotation, so I'm going to add 360 degrees there. So +360. There we go. This angle should be 321.340, and then we're going to round to a 2. So polar form, R, CIS, and then theta. And you can see here the beauty of the shorthand. I don't have to write that long angle value out twice to say cosine of that plus I sine of that. All right, excellent, excellent.